Hello again, and welcome to section 1.5 of chapter 1, which deals with analyzing graphs of functions. So exciting. So what are the objectives of this section? So at the end of this section, you should be able to use the vertical line test, know what that means, find zeros of functions, know what that means, determine intervals where functions are increasing, decreasing, and determine relative maximum and minimum value of functions, determine average rate of change of a function, and then finally identify even and odd functions. So let's begin. The graph of a function. Okay, so we've studied functions from an algebraic point of view. In this section, we're going to talk about their graphs. So what is a graph? It's just basically the collection of ordered pairs x, f of x or y, so that such that x is in the domain of f. So what do we remember? Remember that x is the distance from the y-axis. So if at any point, remember that x is this distance, right? If I was to project it here, it would be this distance, right? And y equals f of x is the distance from the x-axis. So the vertical distance is y, the horizontal distance away from the axis is x. Not too bad. Okay, so what about graphically? What if we want to find the domain and range of a function graphically? So let's go ahead and do that. So let's say you have here a function f, okay? Kind of cool, starts here, does a little up, comes back down, ends here. Okay, let's use this graph to find the domain, the values at -1 and 2, and the range. Okay, so the domain is easy enough, okay? The domain is all the values of x where there exists graph, where the graph can exist, okay? So here, so let me tell you, so here at -1, okay, there is graph. It starts at x equals -1. And it continues and it continues and it continues. And at x equals 5 is an open circle, meaning, oh, it's up to that point, but it doesn't include 5. Okay, so it goes from -1 to 5. That's A. Okay, so I'm going to restate this on the next slide, but I just want to use the picture right here with you. So B, for -1 and 2, so at -1, what is the value of f? In other words, the easier way to put it, what is the value of y when x is -1? So when you see this here, you go, okay, what's f of -1? That just means what's the value of y at this point on a graph. So here, so x is -1, the value of y is 1. Okay, so f of -1 is equal to 1. Not too bad, right? Pretty easy. How about 2? So at x equals 2, f is -3, okay? So f of 2 equals -3. So remember from before where we said function evaluated at that point is equal to y at that point. Okay, and then the range is the lowest to the highest value of y where there exists graph, okay? So graphically think of it like this. So what's the lowest value, the minimum point of this function is here at 2, -3. So the value of y, because we're talking about range, is -3. So it starts at -3, and it goes up, 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 up. Here's the highest point, and what's the value of y at this point is 3. Okay, so now you've seen it graphically. So here, so just to restate what I said, at -1, it's a closed dot, so x equals -1 is the domain, and the open dot indicates that x equals 5 is not in the domain because it's open circle. That means, hey, there's no graph here. So the domain of x, of all x, is in this interval starting at -1, so we'd use a bracket to include it, comma, then it goes up to 5, and we use open parenthesis. Okay, that means don't include it, but it goes everything up to that point. So then for B, so f of -1 is 1 because this is the point on the graph, okay, -1, 1. And also f of 2, 3 is a point, -3 is a point, so f of 2 equals negative 3. And then here, because the graph does not extend below f of 2 equals negative 3 or above f of 0 equals 3, we look at the y's. So the lowest value is negative 3. The highest value is positive 3. So you would say the range of f goes from negative 3, comma 3, and you include those points. Okay, so yes, so the use of dots open or closed at the extreme left or right of points of a graph show that it stops there. The graph stops here. These are stopping points. If you don't have these dots, you can assume that the graph continues beyond. Sometimes in a drawing, I'll put a little arrow to show that it keeps going. So by definition of a function, at most, one y value corresponds to any given x. So remember we said you can't have two outputs for a single input. Okay, so that means that graphically what that means is you can't have two or more different points with the same x coordinate. And so in other words, no 2 points on the graph can be above or below each other vertically. So by that reasoning, a vertical line can intersect the graph of a function at most once. Okay, so if it's a graph, it's a function, you have a graph of a function, the vertical line test, so that's introducing to that just kind of, okay, so the vertical line test is a test to see graphically whether it's a function or not. So here are, the vertical line test says a set of points in a plane is the graph of y as a function of f, as the graph of y is a function of x, if and only if no vertical line intersects the graph at more than 1 point. So these are some, sorry, this is my cheesy drawings. So here you go. Let's say you have a graph of a line. Of course, lines are functions, but using the vertical line test, you draw a vertical line. Yes, this is a function. Here's another graph, looks like some x cubed. Okay, you draw a vertical line. It only hits once anywhere, so yes, that's a function. Here, however, you have a circle. This is a terrible crooked y-axis. And I draw a vertical line. It hits more than once, okay? So no, this is not y is a function of x. Okay. Next, zeros of a function. Okay, so zeros of a function, you can think of those as x-intercepts, okay? So if you have a graph where the graph has an x-intercept at some point a comma 0, because remember, for any x-intercept, the value of y is 0, and then x will be whatever it is. Then you would say, you can also call a 0 of the function, okay? So think of it when I say, oh, find the zeros of this function, I'm basically saying, okay, tell me what are the values of x such that if I plug this x value into the function, I get 0 back, okay? So again, what are the values? The zeros of a function are the values of x that when I plug it into the function, I get 0 back, okay? So they give me 0, the output is 0, you know, or values of x such that the function is equal to 0, that's fine, evaluated at x. Okay, so let's find the zeros of function. Here's a couple of examples. So A, suppose you have 3x squared plus x minus 10. So we've done this, right? We're basically, when you say I'm finding the zeros of a function, that's another way of saying you're finding the x-intercepts, or where the graph touches the x-axis. And how do we do that? We set function equal to 0, okay? So we take this whole thing, we set it equal to 0. So remember factoring, it's coming back up again, it's not going away. 3x times x is 3x squared. The factors of negative 10 are negative 5 and positive 2. And then when we simplify this, right, by zero product property, we let each one equal to 0. So the first factor equals to 0 gives us x equals 5/3. The second factor equal to 0 gives us x equal negative 2. Okay, so then we would say that the zeros of f are 5/3 and negative 2. Okay, so the graph of f has 5/3 comma 0 as an intercept and negative 2 comma 0 as its x-intercepts. Okay, so here's the graph and these are the zeros. Okay, so let's do another one. So let's say we took the square root function. Or this is actually a semicircle, which is a function. So look, see, vertical line test, it's a function because it's been restricted. You take the square root of it. So let's say we let the function equal to 0. To get rid of this square root, we square each side. Okay, now you solve for x, so I'm going to go ahead and add x squared to both sides, and then I'm going to take the square root of it, and I get plus or minus square root of 10 for x. Okay, so the zeros are here, negative square root of 10 and positive square root of 10. Okay, so you have, these are the x-intercepts, right, or the zeros. Okay, and then for the third one, you have a rational function, and we set that equal to 0. So remember rational functions. How do I find the zeros of a rational function? Well, I just let the numerator equal to 0. Why? Because 0 divided by anything, doesn't matter what it is, unless it's 0, of course, will equal 0, right? If you take nothing and you want to divide it into multiple pieces, you get nothing back, right? So 0. Okay, so basically I'm taking the numerator, 2t minus 3 equals 0. Solve for t, right? I'm adding 3 to both sides, divide by 2, and I get t is equal to 3 halves. That's my 0, so here it is. So here's the function, the graph, and here's my 0, okay? And since it's a t, and this is t right here. Okay, so this is the t, because the independent variable is t. All right, so not too bad. Let's talk about increasing and decreasing functions. Okay, so the more you know about a graph of a function, the more you know about that function itself. So let's look at this graph right here in this picture. Now, we read the graph going from left to right, and if you notice, so from left to right, here at negative 2 to about 0, the graph is decreasing, it's going down, okay? From x equals 0 to x equals 2, it stays the same value, so we say it's constant. Okay, so from 2 to 4, it's increasing, right? Because the value of y is going up, 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 up as x increases, okay? So here the value of y is going down as x is going down to the right. So we're reading these from left to right, and left to right tells us decreasing, constant if it stays the same, and increasing if it comes back up. This is really important because you use this a lot in calculus, that concept. Okay, so this is just like another way of saying it algebraically. So a function is increasing on an interval for any x1 and x2. What this means is as x gets larger, right, because the second one is going to be larger than the first one. So as x increases, then the y increases as well. So this is just another way of saying what I just said using symbols, right? That the function evaluated as x increases, the function also increases. So that's the algebraic definition, right, of increasing. And then decreasing, right, would be that as x increases, that's this, it means that the y decreases. So that's why we would say f is decreasing, because literally f is decreasing. The value of f is getting smaller, okay? Now, the function is considered constant if on a certain interval for any two values of x, it's the same. The y's do not change. They remain what you say constant, okay? They remain constant. They do not change. All right, so now that we understand increasing and decreasing or constant, we can start talking about describing the function's behavior. So so for part A, so going from, let's say, since this doesn't have an endpoint, we assume it goes on forever. So let's say here from negative infinity to 0, it increases. Oh, but it still increases from 0 to infinity. So this whole thing increases over the entire real line, the real number line, entire x, the values of x. So as x goes from negative infinity to positive infinity, y is increasing. So this is an increasing function. Now b is a little more interesting, right? So it goes from left to right. If I just look at it, I go, okay, this is increasing, it's going up. It stops here. So from negative infinity to negative 1, it's increasing, okay? Then going downward, right, it's decreasing from here, this middle region. So from negative 1 to positive 1, Okay, so remember when we talk about increasing or decreasing, we're talking about the x interval, right? Over the x interval. So we're saying, okay, so as x goes from -1 to 1, the function is decreasing. Okay, the function is decreasing from -1 to 1. Okay, so at 1, what's happening? The function goes here and then goes up. So then it's increasing from 1 to infinity. Okay, and then from here, it goes from -infinity to 0, it's increasing. From 0 to 2, it's constant. And from 2 to infinity, it's decreasing. Okay, so it goes up, stops, constant, and goes back down. So then just to restate it, the function is, so for part A, it was increasing over the entire line. B, you would write it as the function is increasing from -infinity to -1, decreasing from -1 to 1, and increasing from 1 to infinity. And then for C, remember it is increasing from -infinity to 0, constant from 0 to 2, and decreasing on the interval 2 to infinity. Okay, so to help us decide whether a function is increasing, decreasing, or constant, you can also evaluate the function for several values of x. However, you really do need calculus to decide for certain all intervals in which a function is increasing, decreasing, or constant. Okay, so now I'm going to define some fun terms, some super fun terms, right? This learning about increasing or decreasing is going to help us define these terms, relative minimum and relative maximum. Okay, now relative minimum and relative maximum, it's really basically what it says. Like the mathematicians were not super creative, right? In the naming of terms, the definition's often in the name. So when you say function's relative minimum, that means that that's a point where relative to close around it, it's the lowest point. It's a minimum point, okay? Maximum is a high point, the highest point. So you could think of this as like the lowest part of the valley, and this could be like the highest part of a hill, okay? Unless it's the endpoints. So here, so a function is called a relative minimum when you have an interval where there exists a value inside this interval that everything around it except for that value is greater than or equal to it. Okay, so it's the lowest point, right? So relative minimum, like I said, the bottom of the valley. Okay, so think of a valley, it's like a U, and then the very bottom of the U, that's the minimum. Okay, when you think of a relative maximum, you could say, okay, well, there exists like some x interval, and there's a specific point in it where it's basically the highest. At A, it's higher than every other possible x. Okay, so at a specific A, it's higher than everything else. And let me show you a picture because it will help. Of course, we love pictures. Okay, so here you have this like super fun looking function, has a couple of humps. The relative minima, see it's down here, it's the bottom of the U shape. The maximum is the top of the hill. This one is the bottom of the U, and the maximum is the top of the hill. So relative minimum and relative maxima is the plural form of maximum, okay? So later on, we're going to study how to find the exact relative minimum or relative maximum for a second degree polynomial function. If you recall, that just means the exponent is 2. The highest exponent is 2. But for now, you can use your graphing calculator to find pretty close approximation of those points, okay? So let me show you using my fancy calculator. So here, this is may or may not be a homework problem. I'm not sure. So this is you use a graphing utility to graph the function and approximate to two places any relative minimum or relative maximum. So this is at x minus 4, x times x plus 2. So let me show you. So first thing you do is you go to y equals, hit that, and then you type in parenthesis x minus 4 and parenthesis x plus 2, just like that, just exactly the way it's given. And then you go to graph. Okay, and there's my graph, okay, and you can hit trace. The trace function kind of allows you to see, okay, it's increasing, it's decreasing from there to there. So you can see the values of x and y as the graph changes. So I'm just clicking on the button. So if you look here, so kind of down in the bottom, you get y is equal to negative 8.999. Then it comes back up. So it's approximately negative 9, but you can actually go second, calculate, go down to minimum, and you can hit left bound. So you kind of just do a little bit to the left of the minimum, hit enter. When it says right bound, you scroll to the right of the bottom and hit enter, and then your guess is like right there where you kind of guess the bottom is, the minimum is, and you hit enter, and there it is. The minimum is negative 9, and it's approximately 1, or x is 0.999999998. Well, actually it's 1, you know. Okay, so that's that. So see, it's approximately. Okay, next, let's talk about what the average rate of change is. Okay, so we know that the slope of a line can be interpreted as a rate of change. So for a nonlinear graph whose slope changes at every point, the average rate of change between 2 points, so let's say this is x1, and this is another way of saying y1, remember, function notation, x2 comma y2, or f of x2, f of x1, is the slope of the line through those 2 points, right? So if you have here 2 points, and we call this line in particular, when you hit the graph in 2 places and you draw a straight line, it's called a secant line because you cut it, right? It's a secant line. So you see here, this secant line has a slope. So you have here change in y, so f of x2 minus f of x1, or y2 minus y1, over change of x, okay? So that's kind of how it is. So you have average rate of change is f of x2 minus f of x1 over x2 minus x1, and that's change of y over change of x. In other words, slope m of the secant. So you put a little SEC to denote that it's the secant line you're finding the slope of. How low, we could tell because it's increasing. Okay, so this means that this other secant line is going to be negative. The next one would be the same equation. So f of 1 minus f of 0 all over 1 minus 0. So you would get negative 2 minus 0 over 1. And this slope is negative, so negative 2. So the next thing is even or odd functions. So now we're going to talk about what does that even mean, even or odd functions. So we've studied different types of symmetry, right? Remember we talked about, hey, if it's symmetric with respect to the y-axis, that means you can fold it. If you were to be able to magically fold the plane in half along the y-axis, it would be on top of itself. And to say that something has symmetry with respect to the x-axis, you would fold it down, right, in half, and it would be exactly on top of itself. So a function is said to be even when the graph is symmetric with respect to the y, and odd when the graph is symmetric with respect to the origin. Okay, so if you call it that way, that means you can have a test to tell whether a graph is a function is even or odd. So we define even, we say y equals f of x is even when, for every x in the domain, if I was to plug in negative x into the function, I get the same value that I would if I was to do a positive x. And this makes sense, you guys. Why does it make sense? Because if it was symmetric with respect to the y-axis, the y values are going to be the same. It's the x ones that are different, right? And so that's one way to tell. So what does that mean algebraically? That means, hey, I take the function, I plug in a negative x. If I get the exact same function at the end of it, the function is even. And then if I plug in the test for odd, if I plug in a negative x into f, okay, and factor out the negative, and it's exactly the same as I started with, except there's a negative in front of it, then you would say the function is odd. So let's go ahead and look at an example. So here, so g of x, let's take the function g of x is equal to x cubed minus x. Okay, so if I was to plug in a negative x here instead of x, g of negative x would be negative x cubed minus, and then parentheses negative x. That would give you, so remember negative x times negative x times negative x is a negative x cubed plus x. So if I factor out this negative here, I would get in the parentheses positive x cubed minus x. But what is this right here? This is exactly g of x, right? So when I plug in a negative x, I get the negative of g of x. So that means that the function is odd. Okay, in other words, it has symmetry with respect to the origin. Okay, so how about this function? Let's see if it's even or odd. We plug in the negative x, we get h of x is equal to x squared plus 1. So if I plug in negative x, basically the function is saying, hey, now whatever my input is, in this case it's negative x, square it and then add 1 to it. But what's negative x squared? That's just positive x squared, right? Because a negative times itself is positive. So we get x squared plus 1. But what is this? This is exactly the function that we started out with. So basically what you're saying here, or what we're showing here algebraically, is that h of a negative x is equal to the original function h of x. And because of that, we can say now, hey, this function is even. Okay, I can say that with certainty. All right, so this is the original function. See how it's symmetric to the origin? So if I was to take this piece and fold it down and then flip it, so if I just take this first quadrant here and I flip it this way and then I fold it back, I'll get exactly this, okay? And then the parabola here, x squared plus 1, so this is a cubic function because this is a little 3, right? And then you have a squared function or a parabola, and if you fold it along the y-axis, fold this in half and you're going to have an exact mirror, okay? So that's it for me. That's for chapter 1, section 1.5. Your homework is 1 through 75, every other odd. Okay, good luck, and I will see you on the next video.